Hello everybody, welcome to Physics at Home. In today's lab, we are gonna learn about projectile motion. What is projectile motion? We have a steel ball here and we're gonna put this on the top of a ramp and let it roll down and then roll off the edge of the table. As it does so, it takes off in a horizontal direction, but gravity is gonna pull it down, so it's gonna follow a trajectory. Let's see. So whatever happened after the edge of the table, it's projectile motion, and that is what we're going to study. So the first thing we need is the height of this ramp. So around 9 centimeters. Alright, so height of the ramp is 9 centimeter. The second thing we're gonna need is the height of this table. Okay. Now to do that, I have here a washer. Okay, so you can see this washer here, and this washer I'm gonna attach to the end of a string. Alright, so I have the washer attached to the end of the string, as you can see, and then wherever this is, okay, from this point I'm gonna lower it down. This is what they call in construction a plumb. So when you want to know wherever is the point below which this is, from the edge of the table, let's say you want to know wherever that point is, where we can mark it on the surface of the floor here, then we use plumb. Alright, so right there it stops. Okay, and then I'm gonna let it be there. Get a piece of tape and then wherever it is, so this edge of the tape here is where we can sort of eyeball it, in the sense that this is where the ball takes off, because we want to know the height and also how much farther from the edge of the table the ball lands. So now that we have that, I'm gonna go back here and right there, whatever is the length, the total length is going to be the height of this table, correct? Alright, so let me do that. Okay, so let me measure the length here using a ruler. Okay, so starting from that edge here, so 30 centimeters is right here. Actually it's 30.4, yeah, 30.4 and then 30.4 centimeter, so 60.8 centimeters. And then finally, so 12 centimeters, so 68.8 plus 12, so about 72.8, yeah, about 73 centimeters. Alright, so height of the table, (72.8 centimeters). Okay, so now we already saw where the ball was landing, so let's just make sure get a hang of where the ball is landing. So if I'm looking, oh, so somewhere right here it lands. Yeah. So what I want to do, so wherever this part is, so I want to put a piece of paper on it. Okay. So a piece of paper will sit somewhere on that. Okay. And on that piece of paper, I want a carbon paper. Alright, so this is the side where it is darker compared to the other. So this darker side is where the carbon coating is. And I want that to be sitting on that piece of paper like that. Okay. Now to make this work, make sure that the paper and everything stays at that point. I can just tape it to the floor. So it's now taped to the floor. Stay there. And we can do as many trials as we want. And speaking of trials, we're going to do 5 trials. So let me, as you can see, the paper is right there. Okay, it's blank right now. Alright, so I got everything now. And now I need is, okay. So make sure that I don't want to bump into the table. So now we begin. Alright, so let go. Strong number 1. Number 2. 3. 4. 5. Alright, so we're done with 5 trials. Now let's look at the piece of paper here. So, there we go. I don't know if you all can see, but this right here is all the ball as it lands. It made an impression, a circular impression on that piece of paper. Now, before I remove this piece of paper, I want to measure the distance. From the edge of this tape to wherever this is. Okay. Alright, so let's do that. I could use my string, or I could just do it from here. Alright, so start from 30 is up to this point. So 30 plus 12 about 42. So let me just make sure one more time. Start from here, from the edge. 30 is at this point. Yes. So they are between 12 and 12 and a half centimeters. So within 5 millimeters, we get 5 spots. And the closer is the grouping of all of these impressions, then the better is your, or more reliable is your result. Okay, so about 42 to 42.5. Those are the distances. All right, so let me write that down. So x distance is about 42 to 42.5 centimeters. Okay, now let me remove this piece of paper so we all can see what was going on here. Alright, so right there, you see, those are all of the 5 impressions. They are all piled up together, grouped together. Okay, so that's a sign that they're we were putting the ball at the same exact spot or close enough, and then it was rolling down and it has the same speed as it took off. Okay, so when it was doing that, it all landed on a very close proximity. Yeah. So now that we have done all of this, next up we're gonna look at how to calculate the speed of the ball as it takes off, and that speed is going to be related to the height of this ramp, and we're going to first calculate the speed using the height of the ramp, and then going to calculate speed using the projectile motion. And the speed using projectile motion and speed using the ramp, they should be pretty close to each other. Okay, that will give us our percent error. Here we see the setup for our lab, and there are two parts. The first part is the ball rolling down the hill. This is the part 1. And part 2 is the projectile motion. So let's see what's happening in the part 1. So as it rolls down from height h, it gains some velocity. And that velocity is given by this formula right here. And this formula actually comes from the discussion about moment of inertia and energy balance, as the ball has some potential energy and it rolls down to get some kinetic energy. Now this is a bit ahead of the schedule, all of these points, but we can borrow this equation from those topics. Okay, so if we work it out here, the height that we measured in our problem was 9 centimeters, which was 0.09 meters. So G being 9.8 multiplied by height being 0.09 multiplied by 10 over 7. That gives us the velocity as 1.1225 meters per second. Now this is supposed to be the speed of the ball as it takes or as it comes down the ramp, so at the bottom of the ramp. And since our bottom of the ramp is pretty close to the edge of the table, we are hoping that the speed of the ball as it takes off the edge of this table is about 1.1225, and this is what we're going to verify in calculation of part 2. Okay. So in the part 2, our goal is to calculate this velocity, which we already know from part 1, but we're going to verify how close do we get using the discussion about projectile motion. And as you can see, as it takes off the edge of the table, this dashed line is the trajectory of this ball. Okay. So it's a two-dimensional motion, and in this two-dimensional motion there are two accelerations. There is an acceleration along x-axis, which we're gonna consider as 0 meters per second square. This comes from an assumption that the projectile is under 0 air resistance. Now the height that we measured was about 0.75 meter, or like close to 1 meter. So we will see next that the time of this flight for this ball is very short, and that's why it's a safe assumption that during that short period of time the air resistance doesn't much really affect the motion of the ball. So that's why we can assume that acceleration along x-axis is 0 meters per second square. There is also an acceleration along y-axis, which is negative 9.8 meters per second square. This acceleration is, the pole of the gravity, correct? Alright, so we have the x acceleration and y acceleration. Now what we also need are the x and y positions. So let's call this here, as it takes off the edge of the table, as position 1. Okay. So position 1, we can say that its x coordinate is 0, and so is its y coordinate. So we could consider this as an initial position of the ball, and the final position of the ball is going to be right before it lands, so somewhere over there. And those two x and y coordinates are given by the height of the table and the horizontal range that the ball travels as it lands on the table from the edge of the table. So these x2, y2 are the coordinates of the final position of the ball. And we saw earlier that the height of the table was about 72.8 centimeter, which is 0.728 meters. And since this is below the 0 for y, correct, we are going below 0 y position, so we have to put a negative sign in front of it. Okay. x2, on the other hand, x2 was we had 5 impressions on that piece of paper, and they were all within 5 millimeters, so 42.25 centimeter or 0.4225 meters was the x2 position. Okay. Alright, so now that we have x1, y1 and x2, y2, and then 2 acceleration, now the third thing that we need to make sure of is the understanding about projectile motion. What we know is that as it takes off the edge of the table, the ball is not dropping yet, meaning the initial y velocity of the ball is 0. It has started to drop, correct? But what we do have is initial x velocity. Yeah. So the v1x, there is some value because it is going along straight line, right, at a horizontal direction. This is the velocity that we are interested in, and we are hoping that this here matches the velocity that we calculated in the part 1 of the problem. Okay. All right, this right here now is the setup of everything that we understand about now this problem. So what we're gonna do is use 2 equations, which are just the 2 versions actually of the same equation, and that is x2 y2 equals to y1 plus v1y t half ay t squared. This here is a kinematic equation, y2, y1 as we know, okay. v1y we know is not dropping yet at the beginning of the trip. Ay we know, and time we need to calculate. Okay, so this is part 1. So let's calculate this time here. y2 is negative 0.728, y1 is 0, v1y is 0 multiplied by time, plus half times negative 9.8 t squared. Alright, so this zeroes out and this zeroes out. Okay, so we have negative 0.728 equals to half times negative 9.8 makes it negative 4.9 t squared. And since both of these are negative, we can make them positive. Okay, so now 4.9 goes to the left. So 0.728 divided by 4.9. And this is equals to t squared, right? So to get t, we need to square root both sides. And this gives us 0.385. So 0.385 seconds is the time for the fall. Alright, so we know how long it takes to drop. In that same time, it travels this x2 distance, correct? The range, as we know. Yeah, this distance. So what we're going to do, we're going to use a x version of the same equation that we see on the top, which goes like this. Okay. Alright, so let's plug in. x2 is 0.4225, x1 is 0, v1x we are trying to calculate, time we know, plus 1/2, ax is 0, and time we know. So this term zeroes out, there is 0 in the beginning, so what do we have? 0.4225 equals to v1x times 0.385. Alright, so if we bring 0.385 to the left, gets divided by, and that turns out to be 1.097 meters per second. So this calculation that we did, this is telling us what was the speed of the ball as it takes off that edge of the table. And our earlier part 1 calculation told us what could be the speed of the ball as it takes off the edge of that table. As we can see, these two numbers are pretty close to each other. Well, let's calculate the percent error. Okay, so percent error is velocity from part 1 minus velocity from part 2. Okay, get an absolute value divided by velocity from part 1, because that is what we are expecting, right? That's our reference point, 100, and that gives us the percent error as the 1.1225 minus 1.097, 1.1225 times 100. That gives me 2.27. 2.27%. That is the percent error. Now next, you can increase the height of the of your ramp right here and rerun the experiment so that you get different x2, and then since the drop is the same, we can use the same time that we calculated, so that all we need is the height in the beginning of the ramp. Then we can calculate the velocity from part 1, and then we get x2 by getting the average of the 5 distances for the range of the projectile, and then plug it into this second equation here, right here, and we can calculate the velocity, and we can see how those two velocities again compare with each other. Alright, so hope you enjoyed this video. Next week we will be talking about forces.